Hello, this is Jonathan Templin from Clemson University, and I'm back with another lecture, this time an introduction to regularization methods. This fits into our class a little bit in the sense that it comes after our discussion of linear models and generalized linear models. These methods are more thought of as what we would call quote unquote machine learning methods, although where the limits of machine learning begins and ends is really not well defined. To me, I look at these methods as techniques for variable selection and consideration of how your variable selection methods may impact the generalizability of your results. So let's get into it today. The problem is best fit. You understand in linear regression or in generalized linear models, we pick a model or align the parameters such that it fits best the data. In linear OLS, ordinary least squares, we try to minimize the squared error, that's basically the squared residual, sum of squared residuals, putting a line right in the middle of our point cloud, if you think of it in two dimensions, x predicting y. In generalized linear models, it's a little bit like that, although instead of using a minimization function to figure out what the parameter estimates are, we instead decide to use a maximum likelihood function. So we maximize the likelihood. You can think of a maximum and a minimum in some cases as negative one times the other. They're basically equivalent, but we're trying to find the best fit under some standard. But there's a problem with best fit. Let's get into why. So in traditional research, we had relatively small n, small numbers of participants, and small numbers of variables. And every example in this class, I think, would fall under that similar mindset. The focus was theory-driven hypothesis testing. So trying to understand which variables impact prediction, right? So which independent variables are good for predicting one outcome itself. The new reality is we have quite a bit new data, a bunch of data. It's become increasingly easy to collect data. Now, I will say, if you're a person who collects your own data. There is no such thing as big data. All data sets are big data because it takes a lot. That's a lot of effort to be able to do such things. But the real sense of it is that we can collect lots of data now. You can think of every type of click behavior you have on a screen or any type of um, survey data, anything that comes from your cell phone, wearable technology tracking your heart rate all day long, et cetera, et cetera. We've got a lot of data. So we have a high dimensional set of predictions. Basically, we have the number of variables we could use to try to predict an outcome is quite large, particularly relative to the sample size. So the consequence is that turns out traditional methods using ordinary least squares, linear models, et cetera, struggle to distinguish signal from noise in these contexts. So the status quo for what we're talking about would be the ordinary least squares regression. It's designed for inference in large samples with a few predictors. You might be thinking to yourself, wait a minute, I have five predictors. Is that too many, too few? Cool, you have five predictors. But we've been talking about in this class, it's not just the predictors. Those are five main effects. You might have five choose two-way interactions, for instance. How many three-way interactions? So you may have just five variables you may want to predict with, but looking at the patterns of interactions potentially may lead you to a very large set of variables to predict with. So this also applies even in customary research, is the argument I'd like to make. So current ordinary least squares, we'll just take the linear model aspect, but you can impute in your mind maximum likelihood if you like for generalized as well. It works the same under both contexts. But generally speaking, it's designed for inference in large samples with a few predictors. The objective for us is to, in these methods, is to get unbiased estimates with the minimum squared error, particularly in linear models. And the mechanism is to minimize the residual sum of squares, right? It tries to pass a line strictly through the center of data points. But the trap is when there are many, many predictors, uh, ordinary least squares or maximum likelihood finds spurious relationships by chance. The term that we use to describe that is overfitting. Basically, the model memorizes the training data, basically the data we collect to provide parameter estimates, rather than understanding an overall pattern underlying it. And what we end up getting out of that is a really nice R squared for our data. Well, depending on your research, depends on the area. I've seen some not so nice R squareds, but let's just put it this way. Whatever it is for your full data set will be very high and likely not to be replicable. or generalizable, right? So the problem is we end up getting poor performance on new data. If somebody wants to go and replicate your experiment, that may not be functional, may not be possible. So here's a way of visualizing the problem. On the left, we have a sparse data. We have a low number of predictors. This case, one predictor, one X and one Y. And this would be a situation where we have our status quo itself. OLS works well. But the new reality is that as the number of dimensions, this number of predictors expand, or if you're in a case where you have a ton of interactions, the connections end up becoming too complex for this simple minimization. So basically what we're going to talk about is the word regularization refers to a set of methods, statistical methods, that modify a linear or generalized linear model estimation function so as to really shrink estimates that should be close to zero and find estimates that might generalize better themselves. Regularization is sort of a mathematical constraint that should improve, or its goal is to improve generalizability itself. So our goal is no longer just explaining the past, it's predicting the future. And to do this, we have to make a tough trade-off. We have to sacrifice the perfect fit on our training data. And in this case, again, training data refers to just what we would call data set to begin with. Now, when you get lots and lots of data, and actually as we get further in these methods, what we're going to see is if you think of collecting a data set, maybe we have 1,000 people, 10 variables, right? Up to this point, we would have thrown all the data into the prediction model, gotten estimates on all of it. Now what we're going to talk about is sort of splitting that data into subsets. We might take a sample of that data without replacement, call that a training set. So using a smaller sample, we go and generalize or generate our parameter estimates, and then we see how well they work in the holdout sample, prediction set. So when I say training data, that's what I mean. We have to sacrifice perfect fit or even good fit on our training data to build a model that's robust enough to handle new data. We need a mathematical way to constrain the model to stop it from chasing noise. So this is the solution. It falls under the heading regularization. Again, this is a technique that often gets discussed less so in classes like this, but I think it's absolutely important in this class as well. Plus, this provides a bridge to other machine learning techniques that you may also see as well. So that's why it shows up here. And the concept we're leveraging is something called the bias variance trade-off. Bias is defined as error from erroneous assumptions, like missing a relationship. There's a statistical term in bias. It really means that the expected value of the parameter in the long run is not its true value. Variance is basically the idea that error can arise from sensitivity to small fluctuations in the training set. So depending on that random sample you build to go and build a set of data that gets your estimates, there may be variability there. And the conflict is that in linear models, using least squares, there's low bias, but there's high variance. With regularization, we sort of flip that. It becomes higher bias, so we're going to give up more bias on our parameters, but lower variance, meaning the parameters that we keep are more likely to generalize themselves. So again, looking at this graphic that I made here, on the left, ordinary least squares minimizes the sum of squared errors. And in high dimensional data, it capitalizes on chance, leading to low bias, really accurate parameter estimates, but only for that sample of data that you have. So high variance in whether or not those parameters actually matter going forward. The result is excellent fit to your trained data and poor performance on new data. Overfitting is the problem. The solution itself is to improve prediction, we have to trade unbiasedness for lower variance. We introduce bias, basically statistical bias, to stabilize the model. And this achieving what we call a bias variance trade-off, right? We're going to accept smaller error in estimation, smaller error in bias in estimation, basically to significantly reduce. Sorry, let me back. We're going to accept a small error in estimation bias to significantly reduce the sensitivity to fluctuations in the data, the variance itself. So this sounds counterintuitive. Why would we want a biased model? Right? Well, because in a noisy, complex world, a little bit of bias acts like an anchor. It keeps the model from drifting away with every random wave in your data set. So really what we're trying to do is stabilize estimates so that they appear in more than just the sample of data that you have. Now, what we end up getting from this is a model that's slightly wrong on average, or it's biased, but consistently closer to the truth, generalizing across different samples. Hopefully, then allowing you to provide parameter estimates that will be replicable if somebody else wants to try your experiment or your study later on, or perhaps you want to go and collect more data. So here's how it works. Um, what we do is the following, right? Imagine we have um, we're going to define something called a cost function. If you think of the least squares, the residual sums of squares is its cost. Basically, we want to minimize the cost of being wrong, how far off we are. So that's the term that gets used for this. Now, I will say this part here really relies upon residual sums of squares or potentially the negative log likelihood function. Now, it's negative because when you have a maximum, basically we're looking for the maximum of the log likelihood function is equivalent to finding the minimum of -1 times the log likelihood. Sort of inverts the curve from being convex to concave. Now, what we're going to do is take that core, right? This is what we already had done in our statistics before, our models before, but now we're going to add a penalty, right? It's basically a constraint or a tax on complexity, right? The model wants to minimize error here, but now it has to minimize error subject to this tax. So it has to minimize the tax as well. So the model has to quote unquote pay a price for every coefficient it estimates. So here, let's get into a little bit more specifics. Forgive the math, but math is something that should be our friend, right? Math is power. Knowing math gives you a lot more upward mobility. Let me try to explain this. So in linear models, remember those with a normal error term, conditionally normal distribution, what we're trying to do for least squares estimates is take our outcome y and minimize the sum of the difference between y and the predicted value of y. Here it's an intercept beta 0 plus the sum of each regression coefficient times each predictor. And here I'm going to note P represents a person, so we have n people in our sample, and I represents a predictor. Now, I probably could have flipped that around, but I like P for person. I'm a little weird like that, but hopefully that works through the rest of the notation. There won't be a whole lot of notation in this. I just wanted to show you where the penalty comes from. But again, this is the cost function. We would call in other fields, in machine learning, in engineering, and other parts of science, we don't call this, we call it ordinary least squares, but another term for this is a cost, right? We want to minimize the cost, this cost function, by picking the betas that do that trick. Now, with maximum likelihood, the log likelihood here is basically the log of our density function. Now, that density function is going to depend on the PDF of your outcome. And in a generalized model, that PDF of the outcome could be Bernoulli, it could be Poisson, it could be negative binomial. There's all sorts of distributions it could be. Up to this point in our class, we've really delved into logistic regression, so Bernoulli distributions. But it still works the same regardless of which distribution you choose to use. So now let's get into the penalty, right? So the regression sum of residual sums of squares or negative log likelihood is the cost without the penalty. The penalty itself is a function of the coefficients or the betas that increases as the coefficients grow themselves. And there's different types of penalties that show up. Under the term ridge regression, the penalty is a constant lambda times the sum of squared regression coefficients. And sometimes you hear the word L2 norm. That just means the squared term shows up. A norm is sort of a distance measure. There's multiple versions of distance, and not in getting into too much of this, although we will get back into this in the multivariate normal lecture when we define a statistical distance. This is a version of a distance. The norm is essentially a norming of a vector. And again, this is stuff that we probably don't need to use too much jargon here, but you will see it usually. So I'm giving it to you now. Okay, so in ridge regression, a lambda term multiplies the sum of squared betas. In something called lasso, that lambda term multiplies the sum of sum of absolute parameters themselves. This is sometimes called the L1 norm. And then there's a thing that sort of blends both of them, something called the elastic net, where you might have the lambda, and it is basically taking a weighted average of ridge versus lasso, right? So here, depending on your choice of alpha, like what proportion do you want ridge, what proportion do you want lasso? And we'll talk about why you might pick either in just a bit. Um, Here, if alpha were completely a one, right? So alpha is one, you just end up with the lasso term. And if alpha were zero, you'd end up with the ridge term. Now, if alpha is zero point 0.5, you would end up having a penalty that's sort of a blend of ridge and lasso here and ridge here. So those terms, lambda and alpha, are set by the user. So this is where subjectivity comes in. But it turns out we end up trying out actually a few lambdas. Alphas are sort of picked a little bit differently based on your perception of the structure of the problem itself. And again, we're going to have much more detail as we go forward, but this is the penalty, and this is what differentiates which type of regularization method you're using. But the goal is to minimize the regularized costs. Remember, that's the sum of the cost function for your model plus the penalty by choosing the optimal set of betas. So this symbol lambda essentially functions as our tuning knob, right? If we set it to zero, we get standard regression. If we go back a slide, if lambda is zero, the penalty is zero, and we're left with either linear model regression or maximum likelihood generalized model itself, right? As we turn it up, though, we increase the pressure on the coefficients, meaning that the penalty wants them to be small. Like the bigger the size of beta, the smaller the penalty is, the more penalty it causes. So it tries to put pressure on these coefficients to revert themselves toward zero. So if we turn that penalty up way too high, what we end up getting is we get zero coefficients everywhere. Basically, the penalty takes over. But you'll note the residual sum of squares, that part is still there. So the penalty may be high, our regression coefficients may be zero, but that makes the residual sums of squares grow as well too. So our job is to find the perfect middle ground, somewhere in between zero and super high lambda where there's a bunch of bias, right? So now when we put the two together, our cost function and our penalty, our model actually has two competing goals. It minimizes error and minimizes complexity. And as lambda increases, these coefficients shrink to zero, meaning the complexity goes down. If the zero coefficients there, it's basically saying that the parameter didn't matter at all in the regression itself. So we're going to start with the ridge regression side first. Ridge regression, sometimes called the L2 penalty. The formula adds the sum of the squared coefficients, the cost function right here, and the behavior shrinks coefficients towards zero, but rarely sets them to exactly zero. Sometimes this is called democratic shrinkage, although I don't know how democratic that really sounds. Maybe I'm not fully understanding that reference. Some sort of a interesting way of putting it. It reduces the impact of all variables proportionally, is basically what that's saying. So I guess it's sharing it. Some might say everybody has a penalty applied to them. Is that really democracy? I don't know, but let's just call it that for the sake of being. Now, the way it works is this. If you think of on the left, this is ridge regression. Right here is where your betas want to be, but with the constraint itself, it forces them toward this circle. And the smooth edge right here touches the circle, but doesn't hit the axes exactly. And what we're going to see in a few slides is the lasso works more like a square here, this region here of how the penalty works for each of those parameters themselves. So when do we want to use ridge regression? Generally speaking, when we have variables that have a high degree of what we call multicollinearity. Now, multicollinearity is nebulous topic because really we're talking about complex multivariable relationships, multidimensional relationships. But generally speaking, an example of this could be multiple survey items measuring the same construct. And we're going to see that example again from the chapter that I borrowed for this later on in these slides. Basically, why we're using ridge is it's the master of multicollinearity. If you have 5 survey questions that all correlate highly with each other, for example, our ordinary least squares would panic and might give you wild estimates. The more highly correlated those questions are, the more unstable the results might be. But the ridge basically doesn't suffer from this because it shrinks all of those estimates together, sharing the predictive power among them, right? So it provides a sort of a method for going forward. Now, I will note this example of multiple survey items used as predictors for something else. Um, if they're measuring the same construct, that really should be a latent variable model or a measurement model. We're going to talk about that later in class as well. So this may not be the exact best way of doing it, but for the machine learning world, which I'm not sure that many in the machine learning world are totally on board with what latent variables are, that's a probably a vast overgeneralization, but it's just something to consider. I wouldn't do Ridge here, but it does give an example for it. I would actually prefer a measurement model or a structural equation model in this situation. All right, let's also look at lasso. So lasso again is the lambda parameter times the sum of the absolute regression weights. It forces these coefficients exactly to zero, and it performs variable selection automatically. So when those betas go to zero, it's like you basically kick that predictor out of your model, right? By the way, LASSO is an acronym. It stands for Least Absolute Shrinkage and Selection Operator. And I bet you can see with me stumbling over my words why we abbreviate it LASSO. Right? The small change, right, makes a big difference in how the parameters work. Again, this is sort of the penalty region, right? As each of these parameters goes forward, there's more or less a penalty. But this constraint allows the corners sort of to hit the axis, thereby making some of those parameters go to zero itself. Now, lasso is thought to be best for sparsity. Lasso relies on basically this idea of we're betting that um, only a few predictors are the true drivers of what is a causal mechanism for your outcome. Right now, in social science and education, it's rarely strictly true because there's so many interconnected variables. However, we often aim for what we call functional sparsity. We want a simpler model that filters out the noise, right? The probability that these predictors aren't significant in general samples. Uh, so we can interpret the strongest signals themselves. So what we're left with is a set of regression coefficients that we feel really good about. Now, an example, imagine we have 25 items of big five personality. Uh, basically, the big five. Let's see if I can remember it from my psychology training. Agreeableness, conscientiousness, neuroticism, openness to experience, and E. Mm, extroversion. I think that's it. Call that it. Yeah, clearly not a personality psychologist, although happen to respect and know a few of them. They do good work. But the idea is we're going to have 25 items, basically Likert items, and we're going to go predict some outcome with it. Now, again, notwithstanding, we should be using a structural equation modeling in, a model in this example because each of these indicators, each of these observed variables has what we call measurement error that is not factored into this approach at all. But this provides us an example that we can work with. This lasso function, if we apply that here, okay, this is on the bottom graph, what you can see here. Each of these values right here is a predictor. We also have an education predictor here, let's say as well. And what we end up getting is the X values are the zeroed out predictors. So when lasso is applied, what you can see is it takes values from the circles and shrinks them toward zero. In fact, these small effects here completely go to zero, leaving only the effects that are larger. And again, what you'll also notice in this graph is the circles. Those circles would be our like our ordinary least squares or non-regularized values. All the other values are shrunken toward zero. So it takes a whole lot of information or signal from your data to really make an impact to show that that predictor matters. Right? So what we're left with here, instead of having 25 predictors, is a much smaller set of range of predictors themselves to do the job in the model itself. All right, let's talk about the practical application of these methods a bit. The prerequisite is standardization. The problem is this. The penalty is applied to regression coefficients. And we've talked a little bit about what is the scale of the regression coefficient, right? It's units of y per units of x. But the penalty does not, it applies equally, right? It's just beta. So if you have a beta where the units of x are large and a beta where the units of x are small, the changes in those betas aren't commensurate, right? So we have to standardize our coefficients. So what we end up doing is we standardize. We create z-scores of our coefficients. So the penalty applies to the information themselves in the data, not the units of the variable themselves. Right. And I also note that categorical variables must be dummy coded before the standardization process as well. So that's one of the problems we have. If we just throw raw data into the regularization process, it will select, most likely select values of that reflect the scale of the variables. So for instance, income versus years of education. Income would likely have heavier weight in that sense, whereas education would not because it's on a smaller scale, smaller variance itself. Right. The other thing is, how do we pick lambda? Well, it turns out we have a process. We're going to try a bunch of lambda values. And by try, turns out the package in R, GLMNet, does a great job making this really easy for you. It will estimate models for a wide variety of lambda, right? It'll split your data into folds. We call these segments of your data, basically samples of your data without replacement. So we may have 10 of those. And we test a sequence of lambda values, right? So we basically estimate a model with a given lambda. We use it to provide prediction for the non-estimated or the non-training set. And then that prediction will have a set of mean square error that has variation to it. That's why we have the 10-fold, basically 10 different versions of mean square. So what we have here is our mean square error for each value of lambda. Lambda is across the top of my plot here, right? Well, I guess the log lambda down here, pardon me. And what we're looking for is the model that provides where's the minimum mean square error. That happens to be right here. But you'll see there's error bars around where the mean square error is, indicating how much variation of mean square error there is across the folds of your cross-validation process. So what we end up seeing is a range where we call this the zone of parsimony, which really sounds really formal. But yeah, it's an arbitrary distinction. What we say is that we would like to pick between a set of models where the standard error is somewhere within one standard, sorry, the lambdas are somewhere within one standard error of the smallest value that you see. So the one standard error rule, we don't pick just the minimum. We move to the right of the graph toward more penalty and fewer variables, right? So more penalty is on the right here, and that gives us the simplest value. So basically we pick from the set of, we streamline to a set of, we try a bunch of lambdas, and we narrow that down to a series of those within one standard error of the minimum regression sums of squares, or the minimum cost function. And then from those, we pick the most parsimonious, the most simplest themselves. Why are we doing this? We err on the side of simplicity here. If a simpler model is statistically indistinguishable from the complex one, we pick the simple one. But I will note, this is driven on a whole lot of arbitrary assumptions, right? The one standard error rule, is it rule or rule of thumb? Is it really, people have done research in it. Clearly, it's studied, it seems to work, but it seems to be an arbitrary choice as well, too. Now, we have some extensions we have to talk about a little bit here. First being the blend, right? The limitation of lasso is that the variables are highly correlated. Lasso will pick one and drop the rest. Pick one of the correlated variables, drop the rest off. And that's not good, right? What we do as a solution is to take the elastic net to mix lasso and the ridge penalties. And we use that with that alpha parameter I showed you before, right? An alpha of 0.05 is an equal mix. Now, this will depend on your use case. This will also depend on previous use as well in your field. But basically, the result of this blend is that you'll come up with a system that will perform variable selection like lasso, but also keep correlated groups together like ridge, correlated groups of variables. So that's a good thing to have. Now, there's another problem. You can still get results that don't generalize. So what we can do instead is, so why that's the case is variable selection can be somewhat unstable, right? Depending on your sample size, depending on your sample itself, the characteristics of how you work. So we can change the data split itself, actually, we can show this, right? We could just basically change who's in your training sample. Take a different set of data, different training sample. You may get different results. Actually, we'll get different results. So think of it this way. Let's run lasso 1,000 times on a bunch of random subsamples, and we only keep variables that survive a 90% threshold, right? We only keep variables that have non-zero values 90% of those 1,000 times. And this should be a little bit more robust to the noisiness of the data themselves. So here again, with those 25 variables from the example from before, doing this 1,000 times, the zero point 0.9 cutoff here shows you this set of variables had non-zero parameters in at least 900 of the 1,000 samples that we ran this on. The other challenge that we may have is interactions. So an interaction shows up in your model, you know that we have main effects. So maybe we have an interaction between general knowledge and math on some type of outcome like Eccles K data, right? So the interaction needs the main effects in the model to be valid. We mentioned this in the interactions lecture. If you don't have your main effects, the interaction may be non-zero for one of three reasons. It's truly non-zero, which is the good one, or one of the main effects is also not zero, but the interaction is zero. So we need all this together. And so this is where interactions get grouped into a series of predictions called hierarchical lasso. And let's put this in a little bit of context. Like if you're a learning scientist, interactions are key, right? Does your intervention work for everybody or just high achievers? The hierarchical lasso automates the search for these interactions while enforcing logic, right? It will not claim an interaction exists unless the main variables themselves are also important. So it keeps everything in the model itself. This is a good thing. We have another problem with dummy coded variables, right? Let's imagine you have a race ethnicity variable where you had people declare if they were Asian, Hispanic, Black, or white, or something along those lines. And you dummy code it to where you let the white group be a reference group, and then you have Asian, Hispanic, and Black. You may have a result that wants to take one of these, like the Hispanic group, and shrink its coefficient to zero, thereby destroying the structure of the variable itself, right? So group lasso treats the set of dummy codes as a single block, right? It ensures that the demographic variables stay meaningful, or any type of nominal prediction variable is set together in the same group. Otherwise, your meaning completely changes. So this has been a quick primer on regularization. Quick is the term. What this is a bit of a new standard. Rather than statistical significance, we're looking at high dimensional data with an eye towards generalizability. So trying to embrace the complexity, right? In this new era of data intensive research that we're in, regularization is not just a fancy trick. It's really a necessary adaptation. It allows us to embrace the complexity of learning environments without being fooled by noise. It helps us build models that don't just fit the past, but also predict the future. And that is why I picked it to be in this part of this course as we're going along now. Thank you for listening.